Yeah, I just had one question on the homework.
Okay.
For part 3. So when you're using like the LE way of solving it,
Yep.
using C for L over K of 1, you don't use C in the equation. You just.
That's right. If C is in the if you're using whether it's the Euler or the Johnson, if you're going to use effective lengths, use them all over the place and don't use any C's. If you're going to use the C, don't use any effective lengths.
Well, yeah. So when you use the effective length, then for L over K of 1, you wouldn't have a C in that equation where it's 2 pi squared.
No, because you're just using regular L's. But if you are gonna use effective length, use the effective lengths within that equation.
Hopefully I didn't do anything wrong because I have a lot of jobs.
Really? I don't know. So I don't mind working on the problem itself. I don't have it in front of me. But yeah.
I mean, I converted to KSI, and I just did inches.
Yeah, are we doing in yeah. Is that's a US units one? That's a US units problem.
Yeah, I believe so.
Yeah, no, it's probably not.
Yeah, because I only have one Euler right now. Because Euler you use if it's above L over K of 1.
Yes. Yeah.
So I only have one of those.
Okay. I don't know if I'm trying to remember if I did anything with that problem from like previous problems. I try to change them up every year.
Because
every semester, but now I can't recall.
Well, B is basically what we did in class, that problem.
Yeah.
It's just millimeters.
I usually try to get them kind of a mix, but there might have been 2 Johnsons and 1 Euler, or 2 Eulers and 1 Johnson.
I mean, I just found the weak axis and the strong axis.
Right? Okay, all right.
So maybe that's why. So out of all of them, I only have 1 Euler.
Okay, all right, yeah.
I don't. Out of the 6.
Did I ask for both axes?
I don't think you did. I just.
Okay, all right. That's fine. Yeah, no, it doesn't hurt anything. But it's usually going to bend about the weak axis. It's going to go about the weak axis first. So usually, I think that's what I probably implied. But then once again, I don't remember.
One of my answers is pretty close.
I have attempted to make a problem before where I had. I'm just going to draw it like a rectangle here. I guess I maybe should have made it look weaker on one. Where, and I alluded to this in class, where this is going to be the weak axis right here, if I had drawn it a little bit narrower, I guess. And I've had it before where I like put a cable right in there, right? So
you can't tell which one's the weak.
So now you can't quite tell which one is going to be the weak axis, right? So there's 1 column and 2 potential different failure modes.
Well, yeah, because one of mine I have they're like 50 KSI off of each other.
Mm-hmm.
So I mean, it's kind of close.
It should be KSI, right? Though it should be kilopounds, kips.
Yeah, that's what I mean.
Okay.
So yeah, it's not too far off of each other.
All right. I haven't graded the exams yet, so I don't know. So maybe did anybody? Did I post? Yeah, I think I did post a link to the to me going through the solution.
Yeah, I haven't looked at it.
Okay. So let's see. How'd you do on the other stuff with the deflection and?
I haven't looked at it. Because I started looking at it really after that class, so I was like, well, this is fresh in my head.
Okay, I got you. Okay, makes sense.
The deflection shouldn't be too hard. It's just adding all those stuff.
Yeah, there's a little bit of creativity maybe sometimes. I think in one of the modes.
Because the force is acting along the, I think, x-axis. Then you have, if you want how each part is deflecting, it's like bending.
Yeah. And like in this guy right here, here's the generic one that they have in chapter 4, right? And they're going to use this is where they're using superposition. It's getting a little difficult here because we do have a like the easy one though. No, actually the easy one is in the X direction, and that's fine on here. So we could want to do the X direction one, which would probably be, I don't know, one of these is usually, this is probably a combination here. Yeah, here you go. They did this one right here at 442. This could be like a really long problem, though, by the way. We do all 3 axes with forces in all 3 axes, and it's.
So you have to do like a deflection for each one?
Yes. Yeah.
Each force?
Well, do you want to go through it?
Yeah. So
okay, let's do. This is a tough problem. This is problem 442.
So you do deflection from A to B, and B to C, and then C to
yeah.
X, with D, and then for FX, FY, and Z.
Yeah, it's a little bit of a pain in the ass. But we can just do the big picture thing, and then try to get numbers later, right? But the big picture is probably challenging enough. So I'll try to see this one. Won't get this thing when we go so high. All right, so I'll make my preliminary system. This is going to be problem 442. And I won't go try to go too crazy, but I think we get a good sketch. It's good practice too. All right, and so let's see. We're going to call this A, and this is going to be 6 inches. And I guess we're going to label this. I'll label it the same way they did. It's 5 inches. Oh, didn't make that parallel. And then this one is 2 inches. And we get a force right here. Let's label what they say. They say X is going to be, X is negative in this case. Okay, so they're going to be a little clever. X is 150 pounds. And Y is 0. Okay, so that's not too bad.
Only in 2 directions.
It's only in 2 directions. And then Z is also negative. So it's going to go that way, right there, right? And I don't need to write the negative if I put the arrow. That's redundancy. There could be some problems with this, with anything that would cause like a torsion of this. I also want to go get my notes instead, because I don't really like, we can quickly look at what Shigley does. I guess it's not too confusing, but I think the other one from the other book that I gave the excerpt for is much more straightforward. But this is 1 inch diameter right here. And they're saying this is 1/4 inch. And this dimension is 1 1/2 inch. And then this thing is over here, 3/4 of an inch. Off the page then. I think I got all the information I want. So first thing I would do as part of this, put my head on straight. Let's see, there's Y and there's Z. Here's X. I think I'm going to draw it in the XY. It just feels right. I'm calling it FBD, but I don't know if I'll just put it down there. It says mine. All right, so I got a force coming this way, and we're looking for the deflection at D, right? So I didn't label all these. D, C, and B, okay. And Find the deflection at the tip along the x-axis. That's actually that's what this problem is actually asking for, which isn't exactly too terribly bad, I think.
So it's not worrying about the y direction?
Yeah, they're not worried about the y direction. That's kind of surprised. Yeah. Maybe they're trying not to be too cruel. Problem 443 does ask, but let's try this again. Okay, so we only see the 150 pounds. So in the x direction right here, we're going to have a crushing that's going to take place of this guy. This is A to B. And then we're going to have also from C to D. They're both going to here. So we're going to have like a deflection at D. Oh man, I don't know if I can use that same designation. There's a lot of for the subscripts to try to keep track of this. I could just say, I could just write it out above it instead of trying to play like some clever subscript thing. But it's going to be, I don't remember exactly my subscript routine. I need to look at the thing right here. But I first want to do it because of AB. Because of the compression of AB. I don't know how to write that. AB. I don't know. I'm not sure how to write this one anyway. But anyway, that's going to be AE over L. Is that AE over L? I think so, right? No deflection. Or it's going to, that's the stiffness. What is the deflection of just off the top of my head, I should memorize that. FL over AE. But that's going to be the area of AB, right? So we can get the area of AB, pi over 4, 1 squared. Probably seen this one many times and we'll recognize it, but it's just pi over 4 divided by pi divided by 4. 0.7854 inches squared.
So this is because it's axial?
Yeah, so it's just gonna.
So if it's bending, it would be the FL.
Well, I don't have that one memorized.
3EA. I mean, that's what we did in the example problem.
Yeah, probably. I need to look it up at in the back of the book personally, and I couldn't remember that off the top of my head. But that's going to be the 150, and then the length of this thing is 6 inches, and the area 0.7854. And I didn't look up in the book. I didn't see if they said it was steel, probably. Mild steel. Yeah, so we'll just be lazy and go 30E6 because it's like the most common one to use. A lot of places use 29s pretty often, but we'll get like a small number. It's always a small number. Yes, that's really small. 3.819. Yeah, 20 E minus 5 inches. And then we also want to have the deflection of this little guy right here. So he's going to be the area of CD, and that's going to be even smaller, right? So, because he's only 3/4 of an inch, 0.75 squared pi times 4, right? So we have 0.4418. So trying to get a name to see. This actually should be B. This should actually here be the deflection of B because of FAB. Because of F along AB. I'm like I said, I can't remember. This will be the deflection at D due to the compression of CD. So this would be, that F is the same right there, I guess, X. So Fx, this would be LAB up here, so this would be LCD there, is the area of CD in E. $150, and we might actually want to make this negative. We might want to even call this, be a good idea is to make it negative. Just to remind ourselves. And this one is 2 inches long, and got an area of 0.4418 and 30E6. So 152 times 4418, 30E6 divided, really small, 2.2, and this is also negative, so let's get crushed, 2.263 E minus 5 inches. All right, so I don't think anything is going to happen. No, nothing really matters to us in the YZ plane. So the rest of it's going to be in the XZ plane, looking down at it. And I think I can see right away what the various ones that we're going to have to look at. So, yeah, it's going to be several here. So we got, what, 150, whoops. And we could actually have done all of this axial stuff. I guess we could have done that actually in this view, so that it wasn't really necessary to draw the other view. So everything could have been done because right, we're just pushing down axially in this view. And this is A, B, C, and D. I think it helps when looking through these to kind of like think through different stuff. So one of the first things that I think is that's going to cause a deflection. Okay, there's a couple that just jumped to my mind that are possibilities, so I'm getting distracted as I think through this here. But I'm going to say the bending of BC this way is maybe one of the big ones. It's probably one of the major things that's going to happen to this. So let's say the deflection of C, I want to say due to a moment. Deflection of C due to the moment caused by, damn, I don't know. It's going to go down. And that one we do need to look up. I think he probably said it correctly, but I'm going to look it up anyway. And by the way, I don't know the solution to this problem off the top of my head, so this is always it's always fun, exciting. It's going to be this one, right? Yeah. So that's, and this is simply going to be because of Fx. Right, so this first one is going to be because of Fx, but you might be looking at this 100-pound, and we want to talk about that there. So like the moment, and I'm deviating from what I have done in the other examples. I wish I had that. Like I could peek at the examples and see what they had done here. But this is the equation here. It's going to be F, and I'll say that's X, L, BC divided by 3EI, and that EI, that I needs to be of CB. And it needs to be as a cross section. Do it someplace, I don't know where, good place to put this over here. Maybe I'll put this up here. But kind of drew that weird. It's bending about that axis right there. You see up here? So it's like, it's bending like along there. Kind of like I got one of these guys. It's bending like that right there, right? So because it's being pushed by this right here, so it's the cross section looking that way. So that I of CB is going to be h cubed over 12, and the base is going to be this width right here, and the height is going to be that direction. Does that make sense? Or did I confuse it?
Say that again. So
Okay, it's going to be BH cubed over 12 is memorize this thing right here. But we got to say, is this the base or is this the base? Is this the height or is this the height of that rectangle? For what we're trying to do here.
the long side would be the base.
Yes, yes. Because if we're a lot of different ways to look at this, I think this is going to be the weakest axis. So we don't want the biggest number to be cubed, right? It's going to give a really large. That'll be the larger of the two different choices that we have. Right, so that's just one way of looking at the thing, but you could also just kind of like picture that it's bending about this axis right here. So in that case, this is the base. So the base is 1.5, whereas the height is 0.25 because of that 1/4 inch cubed over 12, and I didn't leave a lot of room for myself. So you got 0.25 cubed and 1.5 times it, and then 12 divided. So that's going to be 1.953 E minus 3 inches fourthed. And so we're going to have 150. And the L of the thing is 5 inches up here, 5 inches long. And we're just, we could start actually, this is something that I would probably end up doing. Wait, should we do it from the center or should we do it from just over to the side? That's a little bit of a, yeah. Because it's not really pinned, it's really kind of like right there. Like you should really kind of take 0.5 away from it and make it 4.5. You know what I mean?
Yeah.
How much of a difference is that going to make? Probably not a lot, but it really isn't. That 1/2 inch of the thing is not bending. It's really kind of cantilever from there. So I might try it, and with many things I just make everything into a spreadsheet anyway. So I'll try it. Wouldn't take me a lot to just try it both ways. And so this is going to be the, down here, 1.953 E minus 3. So I could take 150 and 4.5 divided by 3, 30, 6 divided. So now we got a number that's pretty good here. We might actually be able to measure that movement because it's E minus 3 inches. Okay, so let's see, looking around at this thing. All right, so I can see that there's kind of two that are going on right away from this 100 pounds, like over in this vicinity. One is going to be a very, very small, but it's very similar to this, so we might as well look at it, right? We're going to have bending of CD, bending it of D because of FZ. I don't know, at the moment, I don't know. I wish I had my notes with me. Look and go, oh, here I was nice and consistent with these subscript things, but I'm going to try to, instead of subscripts, you might just want to write out like what it is you're doing, so you can add them up at the end. But this is going to be the same equation right here. But we're going to use, and I don't have enough room, and I'll start a scrap of paper, maybe. I would have left more room up there, but I want f of z, L of CD over 3e, and then I of CD. So I need room for my I of CD.
Hello.
Hello.
Nice to see you.
Nice to see you too.
I'm meeting some students here, but my class doesn't start until 2:20.
Yeah, I reserved the room for like 1 to 2:15.
Okay.
On Fridays, we're doing a help session for a class course.
Nice.
Yeah.
Okay. So we'll go somewhere else
Okay.
for the extra help stuff.
No problem.
Yeah.
Nice to meet you.
Likewise.
Pi over 64. And what do we got? That's 3/4 of an inch. .75 raised to the 4 pi times 64 divided 1.553 E minus 2 inches fourth. Maybe I'll also do while I'm here. I think it's the only one I'm gonna need. Yeah, I think it's the only one I need left is the IAB, which is pi over 64. Yeah, I don't have any torsion going on. That's really fortunate actually, because the torsion would be a pain if you had to do the rectangle one. And this is just the 1 inch raised to the 4th, so it's just pi divided by 64. So 4.909 E minus 2. We get that one a lot.
So if you had to do the torsional, would you just take the moment of inertia, like the square, or would you calculate the rounded off edges?
I would just do it with the rectangle, but I would use the, they have to do, there's a special thing that you have to do. Maybe we'll talk about that after. We as many done as I can think of, right? There's a little bit of creativity going on here. I have to kind of think our way through the different ones that are gonna happen here. But let's see, let's get to this one. Itty bitty amount of bending. Oh, I got a little problem here. Made a little bit of mistake. I was thinking of the bending. This is gonna be in the Z direction. I accidentally was going in autopilot, right? We don't really care about the X direction. So this is so small. You could actually say, okay, so this will be a little confusing here, right? It's going to move in this direction, so it would have technically a little bit in Z, but those are so minute we don't play that game.
Right, so we don't even want to calculate.
Yeah, we don't even want to do that one, but. So that one kind of distracted me. I wasn't. I had I was on cruise control. That's what I was trying to say. But okay, so what this 100 will do to this is act like a moment on the end of this and bend this thing further. So this one is bending it because it's just a force being applied to it. But this one is creating a moment that's going to attempt to bend it. So we have to account for that. Yeah. So that one we will use this scenario right here. Right. So we're going to create that moment at the end due to that 100 times the 2 inches long. So it's going to be, I can do that in my head, 2 inch-pounds of a moment that is twisting and going to deflect this end. And that equation for that maximum is mL squared over 2EI. So let's say the deflection at C due to the moment about C right? So that moment about C, we could do this in our head, is this going to be 2 times 100 or 200 inch-pounds? And that equation, already forgot it. M about C times L BC squared divided by 2EI. And that I is going to be the same I as we had up above for the rectangle. And so we're going to take 200 inch-pounds, and the length, still, that should be like 4.5 squared to 30E6, and then the I was 1.953 E minus 3. So you get like, and this it's still all negative. I don't know why I decided to write negative, but sorry. 1.728 E minus 2. That's quite a bit, actually. Now,
It would be decently bigger if we left it as 5, not 4.5, to take off the.
yeah, it would be, yeah, it would definitely get into the thing. I like to try to see if we're going to do an FEA of the thing, to try to see if I can match it as much. So there's like a certain amount of, yeah, it's kind of for practical, just to take it from bending from here rather than from the side. Because that little part, not going to do much. But I don't know how much of an effect it would have. Be interesting and see if we can get closer. All right, trying to think. Okay, so we got that thing is going to bend out this way. Now,
AB bend.
that's a good question. And is AB bending going to affect the deflection in the X direction?
Probably a little bit, yeah.
Yeah, but how? That's the big question, right? How?
Make it greater. It would be bending.
Well, this thing's going to bend, right? But it's going to have a slope at the end, and that slope is going to affect this, right? So as we're picking the thing out, right? This is going to bend, and it has a slope, and so I don't really want to bend this, but I will. I'll sacrifice it. Okay. Here's our little piece right here, and because this guy is bending down, this drops, right? That goes in the X direction. So what we want to do is we want to get this slope is going to be the same thing as that slope, because this is 90 degrees, right? So we want to get the slope of this thing, right? Since I like to draw little pictures of the thing, right? So it goes, so it's going to have a slope like that right there, and that slope is going to be the same thing as this angle right there is going to be the same thing as that angle. So we're going to take that angle when we find it, and we're going to multiply it by this length, because that's going to be the amount of X displacement that it has. And then the way this thing is bending, it's going to be because it has a moment around the end. So it's actually, let me see if I'm saying this correctly. Oh, it's actually going to be two separate ones. Okay, yeah. Right? So one of them is going to be the force on the end of this. Right? Trying to think that. So this one we could what we want to do all the time is make sure to make little FBDs to try as we're having these like little internal arguments, right? Like, okay, how does this force right here affect this? Well, for one thing, it'll be just like having, transferring this force over to this location. But it's also going to be, because there's going to be like a moment that's been placed onto this thing due to this length. But there's also going to be a moment placed on this end due to this force times this length. So let me think. I don't want to double dip though. What I can do is separate these two parts out. And I have my force right here. I got my 150, and I have my 100. And we could figure out, like right here at the intersection, what is the moment? What is the reaction moment? Because that's what's going to be seen on this piece right here. So for one thing, we're going to have our reaction forces, RZ and my RX. And I might actually want to call those at B, because it's at B in the X direction. But now I'm also going to have a moment. And this one is causing a counterclockwise. And this was also counterclockwise. So this has to be a clockwise moment. M, right there.
You always have to get which direction that you want it to go, correct? Or because if you get a negative, that means
that's true. Yeah. Yes. Yeah. It just kind of. It's just convenient.
Right. Because I kind of like to just do it in one direction, so I don't.
Yeah. That's totally fine. And this is going to be at a moment at B. About the y-axis right there. So what we're going to just know what we're saying here is that's going to be, if that's the forces in the moment here, then the forces in the moment right here are exactly opposite from it. Right? So this is going to be the moment at B about y. Right there. So when we go to figure out what the deflection is of this end right here, it's going to be because of two things. It's going to be because of this guy right here, which I know that's going to be 100 pounds. Right? It's going to what we've essentially done is we've just transferred these loads from this point over to this point. And in doing so, we created a moment. That's like another method of doing load analysis of things. We usually think of those as couples. Right? If you want to, in static, sometimes there's a section of couples, and I don't know if we ever get across. So like a reason why we're doing that is like another way of looking at like how to do an analysis of a specific spot is to take the load at that actual location of the loads, transfer it over, and in the process we create a couple so that's possible.
When we did a torsion in the last mechanics class, when you break. When it changes in diameter or force changes, you cut it at the find the internal force in the other direction, and then.
This is what it used to look like for in my youth, right? If we had like a force right there, but now we needed to move it over to here, what we would do is we would put in.
More arrows.
We would move this force over to there, but in order to do it, we needed to have this force right here to turn that one off, right? And in the process, that was a couple, and that created the moment that was onto the thing, right? That couple that we created right there. That was like a technique to do it. And I think teaching couples is a remnant of that like approach to the thing, but FBDs are good enough. We don't need to play that game. So, which is an extra way of doing it. So, this moment that we're going to find, the summation of moments about B, about the y-axis, is going to be equal to 0. So, we're going to take MBY and we're going to add 150 times 5. and plus we're going to add 100 times 2. So our MBY is going to be equal to 150 times 5. Should be able to do that. 750, I could do that. And then plus 200, okay. So 950 inch-pounds. All right, so we have actually 2 separate things that we have to take care of because of these loads right here. One of them is because of this moment, which is this guy right here. That's the MBL squared 2EI. So I still don't know how to do this the right way. This is the deflection. Sorry. We need to create the angle, the angular deflection. So in order to do that, we write out their equation. We need to be careful. No, it's okay, but we should do it. We should actually use this equation right here. There's no difference, but there could be, right? Just have to be careful. I'm just saying, like, if there was some other like loading thing that we would want to do, we want to take the derivative of this with respect to x, so it needs to be x, not L. Not that it's going to be any difference. So we know that y is mb x squared over 2EI. So obviously theta, due to this thing, is just going to be mbx over EI. Just taking the derivative with respect to x, right? So that theta, due to the moment, so it's going to be, I don't know how to write that out. Anyway, we'll just write it. We'll just find the number. 950 times L, which is going to be 6 inches, divided by 30E6. And the moment inertia is going to be the one with the 1 inch, right? So that's the 4.909 E minus 2. And these are going to be in radians. So 950 times 6 divided by 30E6, and 4.409 E minus 2. And we're dividing 4.309, that's good enough, E minus 3 radians. So the deflection of, and this is really C that's deflecting, that's going to be due to that theta, which is due to the moment, right? I'm really screwing up my thing. It's just going to be the length of BC, this length, and we use the full length, not the 4.5, because that's, this is it's from the center of what is what we're looking at to the thing. BC and times that theta, or 5 times our 4.309 E minus 3. So 5 times that. So we get 2. Of course it's negative, 2.155 E minus 2 inches. But we're not done, because there's also this 100 pounds right here. So it's not only is there a moment here, but there's also a force on there. So we also need to use this equation. Now here's one where we can't take the derivative of this. We need to take the derivative of that. Of course, actually, I think it's going to turn out to be the same thing, but let's do it anyway. So this one, in order to get the slope at the end due to a force onto the thing, I think I'm going to get rid of my clip here. not being helpful. All right, so I'm going to take the derivative of this. Where'd you go? Equation. F x squared over 6ei. No, it is not going to be the same thing. Good thing. All right, so it's going to help me out to 3 f x squared L divided by 6ei. So I'll take the slope is the derivative of that. So we're going to have 3 times that. So this is going to be over 2 now, right? F x squared over 2ei minus, and that 2 is going to multiply by this. That's going to make that 6 go away. We have f x times L. I did that right? EI.
I hate derivatives.
Well, maybe I should have done it in another step. I skipped steps, right? Where I'm dropping this 3 down to the front of it and then turning that into x squared, right? Yeah, so that's why I canceled out that. And then 2 drops down to the front and subtract 1 from there, so it's just x, right? And it's going to have 2 times 3, so that's going to be, we're going to cancel that out, all right? So that force is 100. The x squared is going to be L, actually, right? So that's going to be the, let's see, that's going to be the length of this part right here. Because that's what we're doing, is we have a force that's being placed right onto the end of that. We want to figure out what the slope is. So that's the 6 inches squared over 2, 30e6. And then this is off of the 1 inch diameter one, which has a moment of inertia of 4.909 e minus 2. Start looking at the time, because it just goes so fast. 48 after. Did I get that? I think so. Minus my 100, and now here's 6 squared. That's x and L, so they're right there. And 30e6 and 4.909 e minus 2. And I still, I can actually, this is an interesting thing. Okay, I think I should have, should that be a negative number? I think so. I think it'll end up being a negative number, actually. It'll be okay. So, yeah. It's just that. It's really just that. Okay. 36 times 100 and 4.909 E2 minus and divide 1.222 E minus 3 radians. But now that the deflection though is going to be equal to LBC times that. So it's going to be 5 times that 1.222 E minus 3. So we get 6.111 E minus 3 inches, and of course that's going to be negative. Trying to think of any others. I think we got it all covered in the x direction.
So why didn't we just use the formula for y equals mvx squared? Why do we take the derivative to find the angle? Is that because the force isn't acting on that piece?
Okay, which one are you talking about?
Well, just so when we took the derivative for each, why didn't we just use the base equation that was given? Like for the last one, y equals fx squared over 6ei.
Does that come out to the same?
Well, no, I'm just saying, why did we have to convert to radian?
Because we want the slope. We want the slope of the thing at the end, right? Because we wanted
Oh, because the slope is, or, oh, the area under, alright.
The slope, yeah. That one curve, I mean, that one figure, I think is a really good mnemonic, right? Of having we had the shear diagram, the moment diagram, the slope diagram, and then call it the deflection diagram, right? And we went like, so here was our FBD at the top, and we went down, just down to that right there. So we knew we have this. So then we ended up finding, I'm just about to get this wrong. I think if I get the derivative of this one, no. I take the integral. All of a sudden, I'm getting stymied. It should be something like that. I'm trying to think of why.
Yeah, that sounds correct, because if it was a, distributed load, it would, that would give it right.
Yeah. I'm just thinking of, as I'm coming down here, like, why is that a value that's like so large right there? If I'm integrating from left to right of this thing, why would I start right up there? I don't know. Let me not just, but the idea there is like, we go that direction or we go that direction with this.
So is this always bending, or is it because the forces weren't acting on that member exactly? That were.
Okay, so are you talking about this, or you talking about? Okay. Okay, so we used. All right. I hate to go back to it, but I said this is really the concept that I'm operating on. It's like I'm thinking about what is happening at the end of this beam right here, at the end of this section right there. Well, it's observing, because of the loading over here, locally, it sees a moment and a force. And so therefore, it's going to have a bend, and that bend is going to result in a slope at the end, which is going to be the same slope as this thing right here. So this thing moved from this position to that position by an angle. So that means that the tip has moved in that direction by that angle times this length. Is that clear? Did I clear it up?
Yeah.
So I think, I'm not 100% sure, that we have a fine collection of deformations in the x direction. And maybe this answer's in the back and we could look it up and get that great satisfaction, possibly. But maybe not. So we had, they were all negative, so I'm going to leave the negative off. 3.820 E minus 5. Remember, that was just because of compression of the bigger of the two, and then we had one that was 2.263 E minus 5. And then we had, we were bending the rectangular thing, so that was actually a fairly larger E minus 3. And then we had the moment on the rectangular piece, 1.728 E minus 2. Yes, sir.
Anyone show up?
I didn't see anyone show up.
Okay. If you do see someone, don't throw anything at them.
I usually don't too much.
Don't throw.
I reserve that to my own students.
That's prudent.
I think so.
But we're just across the hall.
Okay.
Yeah.
Awesome. Thank you. I don't know why I said thank you, but someone at some point in my life was much politer than I am, and it kind of took. I don't know. So this is probably the largest one here, 2.155 E minus 2, and that was because of the moment creating a bend. Yes, bending deflection. No, that was this one. This one was because of that slope. Yeah, of the bending. And then this last one was 6.111 E minus 3. Right? Sure. Okay, so let's try to get a number. So we have 3.82 E5 and 2.263 E5 and 3.84 E3. They look all up now. Get distracted. 1.728 E2. 2.155 E2 add, and then 6.111 E3 and add them. So I say that we had 4.884 E minus 2 inches is the deflection in the x direction. We're almost done here. Let's see if this one's in the back of the book. This is problem 442. Could be lucky. And if it's wrong, then just cry. That's all I do. I'm just gonna sit here and cry. 442. You bastards, they have 441 and they have 443. But one of the perks of being a professor.
You can say that they're wrong.
Yeah, that's actual. Well, okay. Amongst the perks, as I could arrogantly declare that I'm right and you are wrong. I don't usually play that card because I know it's not true. But one of the perks is that you don't have to go to Chegg to get the solution manual. But actually, I have a Chegg account, so sometimes I actually use their solution manuals. I don't want to admit that out loud. But here is the official Shigley solution manual.
Chegg isn't a bad resource to just look at. Oh.
Yeah, the sad thing for me though is there's lots of professors that aren't taking the time to write problems, and so they're just going through and then you even see professors that just give out the solution manual as the solution, which really stinks because solution manuals are often not written by the authors themselves as their graduate students are already the solution manuals. That's not true for all of them, but for many of them.
But it's also like they're different, different people use different locations for things.
Yeah, different methods. Okay.
The amount of people that are just wrong on Chegg too, it's like.
Yeah, it's a little frustrating. And I hate that I write my own problem and it shows up on Chegg. It just kind of gets me kind of like a little offended. It's like, hey, wait, I went to a lot of effort to write a problem because I think, obviously I had some motivation. All right, so I don't know if I can, because I'm looking at the time right here and I don't want to steal any more time from. I don't know, what time does this supposedly end?
I thought 2, but I have no idea.
I'm not sure if it's 2 or if it's 2:15. But anyway, we'll finish up. All right, so we had the theta at B was 2.307. Does that look like any familiar for any of ours?
I think we had 2.1.
Yeah, they got quite the thing going on here. So I'm wondering what that is. Look at IB, right? So this is really the theta at B. So they might be combining both of them. So I think that's what's happening right here. Okay, so we did them in two different things, but I think they're saying this and this. So you see what that is? Yes, that's what they did. Right there and there. So we have the force at the end of it and the moment at the end of it. So they did the same thing as us. They just, let me put it this way. Oh, I gotta do this first. Right there. So I think they're just adding those two together. If we were to add those two things together, maybe, or actually ours is a little bigger. I don't know. No, I don't know. Let's study it a little bit more. Yeah, ours is a little bit bigger for some reason.
If I add those, I get 2.76 e to the negative 2.
So I don't know why we're different, and I don't think I have the time to look.
It might possibly be that they use, 5 or the 4.5 for the, I don't see a 4.5, so that might be the difference right there. So they use the whole length.
Yeah, they used 5. Yeah, oh, maybe I used 6. Did I use 6?
No, you used, well, no, I'm saying for like the,
No, I did use 5.
no, I'm saying for like the, bending in the X due to the 150.
Uh-huh.
We use that 4.5 because of, it won't bend at the, where the,
I hear you. I'm just looking at this first one right here, and this should be the last one that we just did, right? So they're looking at the slope at B, like we had, and then they're multiplying it. So I must have done. I have the suspicion I did something wrong. Mine's much larger than theirs. Is all I'm saying. I'll look at it some more, and maybe after the thing. Let's look at the final number. Let's see how far off we are. At the elongation of D. Oh, wow. Oh, there's a couple more in here. There's actually an elongation of CD due to tension. That doesn't make sense.
yeah.
It's because of compression.
Yeah, it has to be compression.
Yeah. I'll upload this solution here. Give it a chance to take a look at the thing. Although they're overall, this is much bigger. It has much more here. So I'll try to reconcile on what these are. I'll rationalize and say this is more of a journey than destination type of thing that we're doing here, is to really think through these problems right here. But it's also a demonstration that I don't have all the answers. I have the answer key though. All right, so that's it for today.
I wanted to attach to the end of this to kind of show why we had something different, why I had different things than, if I can get this stupid thing to go away. There you go. How about this guy? Can I get him to go away? There you go. All right, so here's my work right here, and I wanted to compare it to what the solution manual had. Okay, so I had the same, this right here is the same thing that the solution manual got for. That was easy enough. That was just the crushing of this. They're calling it tensile. Let me see, I'll go to the, here's the solution manual right here. So they got the same thing right here, right? So they're calling it elongation, but it's crushing. I don't know why they're calling it elongation, but I got the same value. And down here, here's for that little small little part. Okay, so let's see. I left out this cube right there, so that changed my answer. So that was a significant difference right there. And there was a whole lot of bending. That's the bending of this piece. And I also used 4.5. I think theirs right here is where they get their deflection. And so there's going to be some of the biggest differences that we have. They used 5 right here. So that's one of the biggest differences that we had. And then also I did some math wrong right here. So this is the moment that's because of this 100 times this distance right there, which in fact actually should be like cut down just a little tiny bit, like by 1/8 of an inch, right? Because that's acting right there, right? Because that's good. So that's going to be a moment that's around the end of this that's going to cause bending of this piece. And once again, I used 4.5, and theirs shows up like I'm not 100% sure that they did this one. Okay, so I don't think they did that particular one, right? So they didn't do that bending of the thing. But what they did do, they combined, all right, so back up to like right here. So, okay, so I think that they should have put in a little bit of bending of that end, which would have created a little bit of slope. Not a little bit of slope, but a little bit of deflection, right? It was a moment on the end of this piece that bent it. So they did, I don't think they included this piece right there. But right here, you'll see I have 950. That appears on the end of this, which is causing a slope, and that slope is applied to this piece right there. So that, a little of it shows up right here, right? They're saying that there's going to be a slope onto the end of that. There's 2 times 200, so there's that 200 right there. I'm sorry, that 200, because you see right there is their MB. So there's part of that, and then there's another 5 times 150. So that becomes 750 right there, and 200. So there's their 950, and that's where it counts for. And then the last thing that I think is different here. Yeah, okay. So I'm just using this. Yeah. So here is, once again, I use it as a force on the end of the thing that was causing a slope, and then we had this 5 times those radians right there. And once again, they kind of mixed this up. Here's your 5 times that the radians onto the thing, but they also did it down here. So they had 5 times the radians. So when everything was said and done, if I just left it the way that I had it, and I used the correct, math, and used that cube in the right spot, I get 0.1401 inches, and Shigley has 0.749. But I went ahead and did a SolidWorks simulation on there, and kind of right here in the center, which is where you'd be measuring it from. You don't want to measure it from right there or here at the edge. It's just going to be at the center. I get 0.15, right? So I'm actually closer than Shigley, and I think some of the biggest difference right there, for one, is in that 4.5, because as I said, this little section right here, that 0.5 inches, that doesn't bend. It's only going to start bending right there and where the circle meets it. There's lots of other things that are going to be different between reality, or between the simulation and the hand calculations. Some of them are like in this joint, like what's actually taking place there. Is there some stiffness? Is there some additional stiffness there? Or is there some like maybe additional flexibility? It's kind of hard to say because of what's actually taking place in between. But this exercise is definitely very good to try to show you the how it's more complicated than what it might first appear, than what from a simulation or from a hand calculation. And trying to get them to match real world that's real tough. But I tell you what, if you can do that, if you can get an experiment to match up with the simulation and your hand calculations, then you got a lot of high degree of confidence, then you got the right answer, obviously, or that your methods are correct. I guess maybe that's your high degree of confidence, is that you're proving that your methods are correct. But that really is validating your procedure. And then what you would do then, the reason why you might do that is because now you're going to try to use some, maybe if you're trying to prove your simulation software is appropriate for the application, you do it for a simple thing that you could actually measure, and then you might want to extend it to a more complicated thing where you can't actually build it and measure the thing, but you can do a simulation. That's like the method of validation. It's really kind of an important part of being an analyst or using analysis software. So there you go. I think it was a pretty good exercise. So hopefully this might help with homework or something. Maybe just learn some stuff.